Oh, no. Okay, cool. That's given us an extension. So, and then I'll hide that. So now this should. Yep.
That's good.
Yeah. It's okay.
Okay.
We'll give people a couple of minutes of
Sorry,
grace.
I missed your key.
That's all right. You're teaching at the same time.
Yeah, teaching.
Yeah, can't avoid that.
Tuesday, Thursday.
Yep.
9:45 to.
Yeah. Have you got time after this to go for lunch? You might see if people want to go over and have lunch afterwards. Yeah, sure. Go. Welcome everybody to the IE seminar for this week. And it really gives me great pleasure to introduce Gigi Wang to you today. Gigi is a broad scientist working across many areas of groundwater, surface water interactions, effects of climate change, interactions between land and soil, soil vegetation interactions, stormwater, which he's going to primarily talk about today, and just general watershed hydrology. He carried out his Bachelor of Science and his Master's at Tsinghua University in Beijing, then moved to do his PhD at Iowa State, which he finished in 2001, almost exactly the same time I finished mine. He then was an assistant professor at Tarleton State University before moving to his current role, where he was an associate professor, then professor at Old Dominion University, which is in Norfolk in Virginia, a very, very pretty part of the world, for those of you who haven't been there. He also has a special term professor role at the Inner Mongolian Agricultural University in China. Gigi has won numerous awards for research and for particularly his inspirational teaching and mentoring. He's extensively published in high-quality journals with more than 180 papers, many of which have been cited more than 100 times. and he's been editor-in-chief, guest editor, and associate editor for several journals. He's also been very active in the field of producing influential undergraduate textbooks. In fact, I don't know how you do the amount of work you do with terms of producing undergraduate textbooks. And I have several of them that he's brought with him that I know that we'll certainly be aiming to apply into our undergraduate courses. In particular, and the reason that he's here with us today is that a couple of years ago, beautifully timed to be just before the start of COVID, University of Canberra joined the Fulbright scholarship scheme. So we now have Fulbrights moving from University of Canberra to the USA and from the USA to here. And Gigi is one of the first of the Fulbright scholars to come here and be hosted by the Centre for Applied Water Science, where he's working with us on applying and refining eco-hydrologic models for Australian dryland ecosystems. But that's not the sort of stuff he's going to be talking about today. He's actually going to focus today on his urban water work, and I will, with great pleasure, pass over to Gigi.
Okay, thank you. So good morning. It's my great pleasure to have this opportunity to exchange views with world-class scientists here. So I noticed that you have wide range of backgrounds and try to study water from different point of views. So that's very important because water is so important, but we can't understand water from one direction. So we need to understand water from 360-degree directions. So today I will talk about this stormwater management using low impact development devices. This is my outline. First, I will briefly talk about my mission here, because some people ask me, why do you here? So I will talk about what is my mission. Then I talk about the causes and concerns of stormwater, because we talk about stormwater. Why we have this stormwater issue, and what's the reason to cause this stormwater issue, and what we are concerned. Because it is what, why we concern stormwater. We concern stormwater. Another one is about rationale of stormwater management, because stormwater is the issue. We need to manage. So what's the theoretical thinking or theoretical background to understand how to best manage stormwater? So that's my third topic. And then I talk about this commonly used LADs, that's represent low impact development devices, and hydrologic processes. Because in order to manage stormwater, we need to understand this hydrology process. What the hydrology processes are changed. So how can we modify or restore these changed processes? So that's I will talk about. Then I will talk about this commonly used 3-layer model to analyze LADs. Then I will present this 3 research examples. So we did 3 projects in the past years and related to this stormwater management. Then I will mention this emerging research needs. So what type of research needed to better manage stormwater? Then I will draw conclusions. So that's my presentation today. So I will give a brief self-introduction. So Ross already introduced a lot about my background. So currently I'm a professor at Old Dominion University in Norfolk. Probably some of you didn't know Norfolk. Norfolk is a very important Navy background, Navy base. So lots of these Navy warships need to be built and maintained in Norfolk. So this Old Dominion University, that's roughly 3 hours, 30 minutes driving from Washington, D.C. So this is Washington, D.C. here. So that's a 3 hours, 30 minutes driving to Norfolk. And this side, probably some people, this is Richmond, so that's capital city of Virginia. and southern, that's North Carolina. So Norfolk is located here. So my research interests include effects of climate change versus human activity on water resources, because we know both climate change and human activities could affect these hydrology processes, could affect availability of water resources. Sometimes people cause contamination. Probably most of you are studying these contamination issues. So I will look. My interest is to look at the relative impacts of climate change and human activity on these water resources. Second research interest is water, soil, vegetation nexus and equilibrium in changing climate. Because we know this is a very important ecosystem. So water, soil, vegetation play very important roles in maintaining this ecosystem. So I'm trying to understand how these three things interact to affect this land degradation in desertification process. Also, I study this watershed hydrology, groundwater issues. For example, currently I'm doing a project to look at how sea level rise affect shallow groundwater. They are also interested in studying these stormwater issues. So that's my research interest. My teaching interests include water resources hydraulics. I teach undergraduate and graduate level courses in this field. Urban stormwater hydrology, water resources analysis methods. So that's a larger scale analysis method. Also, I teach groundwater classes. So my mission at ODU, at the UC, is to promote US-Australia mutual understanding, because this mutual understanding is very important, so that the people can talk on the same page, right? So I noticed that something difference between the two countries in the past days. So I'm mentioning coupled. For example, Australia has very good trails, walk trails, but the USA don't. So if you go to USA parks, they don't have very good trails. So also the sidewalk here, that's contiguous sidewalks. You can walk along this very large street, but the USA that's fragmented because they have a sidewalk build, and once this landowner doesn't want to build this sidewalk, that's just a stop. You have to jump to another side. So very not easy to walk in US. So also here we can see lots of people walking on the street, but the USA sometimes just myself. So just one person. I feel scary because the USA many people have guns. You don't know who could do something where you walk on the street. So that's sometimes scary. I also from this Fulbright orientation, I heard some people say Australia people are very pay attention to the title professor, so you call professor. But if you go to USA, in universities, students just call doctor one, doctor is so they call the doctors. Here they call professors. So that's a different. Because in USA, some people say because a professor title is temporary. Today you are a professor, tomorrow you work for government, you are not a professor in it. But the doctor, that's a permanent. So if you own a doctor, that's a permanent, always belongs to you. Wherever you do, you can be called a doctor. Right? So that's a philosophy there. Also notice the others probably the politics. If you turn on the TV in USA, most times they just blame. They don't debate the problems. They don't offer good solutions to the problems. But here I watch the TV programs, the politicians really debate. So they offer solutions. So they talk about this advantages, disadvantages of the different solutions. So that's very good, very good. Hopefully USA will go back to this debating environment. So otherwise they just blame without solving anything. So I will not go through this list. Hopefully I will develop more longer list for this mutual understanding. Also, try to exchange research ideas. So I'm working, try to communicate with different people here so that we can exchange some research ideas. Also explore possible collaborations. Currently, USA has a program to support US students to study abroad. So I'm thinking if we have a possibility to submit a proposal together to bring USA students to here so that we can do some collaboration with research. Then conduct collaborative research, of course. Right? On the opposite side, I saw many Australian people will go to USA to do the same thing, promote mutual understanding, to do collaborative research. Hopefully, if you are interested in this, you can go to the website and submit your application. So that's very good opportunities for people to go there to stay several months to understand how the people do research there and what's the culture there. And also I mentioned these tips. So if you go to USA, everywhere tips. So if you need a service, you need to pay tips. You take taxi, pay tips. Go to the restaurant, tips. I had a statistics professor, Dr. Cook. She's from Australia. She said that at the beginning she was frustrated by these tips because different places expect you to pay different percentage of tips. So she decided to study the statistics pattern of tips across the USA. So that's one of her research topics. So that's interesting. So let's talk about stormwater. So what are the reasons for stormwater? The fundamental reason is that we changed the landscape. So that's the main reason, the fundamental reason. Because originally we have this forest, grassland, we have lots of wetlands, and also we have this varying topography and soils, that's natural soils. And but due to this urbanization, due to our human needs, so we converted lots of land into urban areas. That's paved residential areas, and also we have highways, roads, and also we filled lots of wetlands, swamps, and also we make the land much smoother. So all these factors caused these stormwater issues. So that's a fundamental reason. But we can't stop doing this because we need to live. Right? People need to survive. We need to have a better house. We need to have a better road to drive. So we can't tell people, say, you can't develop land. Right? So we can't do that. So the concerns of stormwater is that the peak discharge is increased. So if we look at these two hydrographs here, for a given storm event, so the blue one is a hydrograph generated by this storm for natural condition before we develop land. And this is red one, that's for the hydrograph after urbanization. So you can see this peak discharge is dramatically increased. That's because we make the land smoother, we filled these wetlands, swamps, so we reduce the storage. So all these reasons caused this increase of this peak discharge. Also the intermediate flow is reduced. Most time we have this overland flow. Overland flow means after rain, the runoff flows on the surface of ground. But the good hydraulic condition is that the rain should infiltrate into shallow soil first. Then this water return back to stream through this shallow soil. So that's a good condition. But currently, due to this urbanization, most of this intermediate flow will be converted into overland. So you can see this percentage of this overland flow will be significantly increased. Also, this base flow is reduced. Base flow is so important because during dry season, we don't have rain. But if we have sufficient base flow, we can maintain the river ecosystem. But once we lose these base flows, then all this river ecosystem will be damaged. The fish will die, and this wildlife can't survive. Also, the timing. So if you look at the timing, so that's it will be earlier. So the peak discharge will occur earlier. So that's reduce the people's preparation time to prevent flooding, because after rain, then this flow will increase dramatically, very quickly, and we don't have time to prevent. Even for evacuation, we don't have time. So that's could cause these lots of damages. So the reason for this increase is that traditionally we have this kind of city settings. So we build a lot of these buildings. We have lots of roof, and also we build the driveways, sidewalk, parking, street, and this runoff from these surfaces partially will be discharged into grassy areas, open space. But most of this runoff will be collected, discharged through this storm sewer system into waterways. That could be river, could be lakes. So in order to minimize this impacts, urbanization, so we could introduce this kind of devices. So we call these devices as low impact devices, so that we can treat this runoff from these different surfaces. Also, we can reduce this direct discharge through this storm sewer system. So we have this runoff reduction facility, and also these facilities could purify water, right? Could remove these contaminants in the runoff. Then after these contaminants are removed, then we can discharge back into these waterways through this storm sewer system. So that's a basic idea to mitigate these side effects of urbanization. So we have 5 ideas to do this. First one, we need to keep rainfall as close as possible to where it falls. So we don't want to accumulate. So if this rainfall occurs at this site, hopefully we just treat this rainfall at this location. So we don't want this runoff to flow long distance, then we have facility to treat this runoff. So that could cause a lot of problems from this origin of rainfall to the treatment facility. So that's the first idea. Second idea, we want to infiltrate as much rain as possible. So infiltration has lots of benefits. That could reduce peak, could purify water, because the soil is the best filter to remove these contaminants. So we want to facilitate infiltration. Also, we want to bite off rain in small chunks so that these LADs or sites are small and numerous. So traditionally, we build this concentrated treatment facility. We build a very large detention pond or retention pond. We collect the runoff from this large drainage area. Then we treat this runoff at this concentrated facility. So that's not good. So based on this low impact development ideas, so we want to build lots of smaller facilities across these drainage basins so that this runoff will be treated piece by piece, not concentrated. Then after development, a site is kept as close as possible to its natural hydraulic condition. So this means we wanted to make this post-development hydrograph close to the natural hydrograph, just like so in the previous slide. Now use LADs to keep pollutants on site as much as possible. So we want to keep these pollutants generated at this site, just treated at this site, not sent to the downstream. So these are 5 ideas for this stormwater management. How to do this? First, we maximize development attractiveness. So currently we build these straits from south, north, and east, west. Straight. So that's good for transportation, but not good for stormwater management. So we want to have this conventional street, but people may be lost. But it doesn't matter. We have GPS today, so that's not a big concern. So it's better to have these convenient streets so that we can increase this flow path length, and during this flowing process, the contaminants could be removed and the flows can be reduced, and some water can infiltrate, some could be evaporated, so that we will reduce the problem for the downstream community. Then minimize peak runoff rates and volumes leaving a site by infiltration. So infiltration is so important. So we try to infiltrate as much as possible. Maximize reduction of pollutants leaving a site. Then minimize construction, operation, and maintenance costs. So we can't build lots of facilities, need lots of maintenance. So we have to design these facilities smartly, wisely, so that we don't have to maintain these facilities very frequently, or we have to spend lots of money to maintain the facilities. Use LADs as an opportunity to educate citizens. So that's very good. So to create some education programs for publics to manage this stormwater. Because finally, we have to rely on residents to manage this issue. As researchers, we kind of go to each family to tell them how to do it. So through these facilities, we can educate them about this, how they should do on their backyards, on their properties, to manage this stormwater. So commonly used LADs, so we have this, we can classify them into 3 types. First one, that's harvesting. Harvesting LADs means we collect stormwater, then we reuse this stormwater. So that's a harvesting type. Harvesting type, usually we have this green roof. So green roof, we use the green roof, we collect the stormwater for flushing toilets or some for vegetation to use. So that's harvest. We harvest the stormwater. Also rain gardens. So we have these rain gardens outside the houses, outside the buildings, make this living environment very well. And at the same time, we can harvest this stormwater and to support this vegetation growth. Rain tank. So we can install these rain tanks to collect the stormwater to water these grasses or water these vegetations. So this is harvesting type LADs. And also we have infiltration type LADs. So for example, we build this infiltration trench. So sometimes if you look at this, some places they have this, it seems there are lots of gravels on the dry trenches. So in fact, those trenches are designed for infiltration. So the stormwater flows into trenches and just infiltrating into ground. Another one that we use this porous permeable pavement. Currently, we already have this permeable concrete, permeable bricks. So we could use this kind of materials to build this street, parking lots to facilitate infiltration. Also, we have this hybrid LADs. That means a portion of this stormwater will be reused, portion of this will be infiltrated. So that's a hybrid. So all these LADs will be used to reduce peak discharge, reduce the ratio of overland to intermediate flow. So we want to increase this percentage of intermediate flow because this intermediate flow has a much better water quality than overland runoff, and also this could have gradually flows back into the river, not just suddenly cause this increase of the flows in the river. Also reduce runoff volume, so that could reduce contaminants, because once we reduce the volume, then we can reduce the total loading, right? Total loading of contaminants. Increase the lag time, so let this peak discharge occur not so early, right? After we have a heavy storm, and so that we have time to prepare. Right? You have time to. So these are LADs. So this is just to illustrate what rain garden, what infiltration trench. So this is rain garden. So if you go to USA, if you go to campus, most of the buildings have this rain garden surrounding the buildings. And this infiltration trench, most time this is shopping centers. So they build this infiltration trenches along some areas of the shopping centers. Porous pavement, so the porous pavement, and this vegetated swale. So this make the street looks good. At the same time, these swales can harvest this stormwater and also can facilitate infiltration. This is green roof. Some campuses, so they have this green roofs. My university does not have, but another university at Norfolk, they contracted this green roof building. So it looks very good. They can harvest a lot of stormwater. They reduce the water bills to flush toilets. So that's a lot of benefits there. And these are rain barriers. So USA in cities, they installed a lot of these barriers to collect the stormwater to water grasses, backyard, something. So as a researcher or engineer, they need to understand these hydrology processes inside these different facilities, because they need to design. They need to figure out the size, figure out the thickness of different layers. So they need to understand how much modifications needed to correct this modified hydrograph. So this green roof. So usually we have this first layer. So this plant, usually that's a plant, right? Then this soil layer. So this provide this growing environment for these plants. And also we have filter layer. So this prevent the pollutants to be drained through this third layer. So that's could be drainage layer, or sometimes we have this sponge-like materials to store this water in this layer. So if you look at the hydrology processes, we have interception. So this plants could provide the interception capacities for the rainfall. And this intercepted water will be evaporated back into atmosphere. And this after this interception, we have this infiltration. So that's we have soil layer. It's infiltrating into the soil layer. And if this we got a larger rain, probably we have this discharge from this first layer. And then we have this retention in this bottom layer, and probably we have some drainage. So if you design some drainage system at the bottom of the layer, and the water can be drained. So that's a major hydrology processes in the green roof. Rain garden. So again, we have this interception, and this runoff from the roof will be collected into these rain gardens, and the portion of this infiltrated. If too much water, then we have this discharge, but this will provide some routing process. Routing process is very important because that can make this flows smaller, because it is needed to flow slowly through this rain garden. Then this we will reduce this peak discharge. Then this we have this if we have this another layer that's connected with the native soil, so we provide this percolation, so that's infiltrating into deeper soil, so we call it percolation process. So that's a major hydrologic processes in garden. Bioretention pond, so we collect this runoff from roof building roofs, and also from driveways, sidewalks, collect this runoff from this one, and this provides this infiltrating into the soil, and this ET process that can evaporate, can transfer, can be used by vegetation plants. Then we have this percolation process. Then probably if we get a very heavy storm, we have some discharge to the downstream. Basewale, again, we have this runoff from different surfaces and infiltrate. If we have this drainage system installed, we have this tile drain system, so that can provide this drainage outside the bioswale facility. So these are major hydrologic processes for different LAD devices. So some people say, how much harvesting LADs do I need? How much infiltration facilities do I need? So we need to know this this amount of the different type of LADs needed. So through many studies, some people developed this triangle relationship for different type of this LAD devices. For example, we just look at this infiltration trench. Infiltration trench can reduce 75 to 100% runoff. So depending on the size of your infiltration trench and the design of your infiltration trench. So we could treat 100% overland runoff. And this one, that's a permeable pavement without this other drain. So that can provide probably 85 to 100% treatment of the runoff. So that's very effective. So these facilities are very effective to treat overland runoffs. For harvesting devices, so that's this edge of the triangle. So you can see this rain tank can collect probably 60 to 100% of the runoff. So this can provide this depending on the size of the tank. And most time we have these hybrid devices, so that could provide some percentage infiltration, some percentage harvest. So when we design this kind of facilities, we need to know this percentage needed. So that depends on your development level. Development level is measured by this runoff coefficient. So if you have a very high level development, the runoff coefficient will be larger because you have lots of impervious surfaces. So that's a runoff coefficient that measures the percentage of rainfall to be converted into runoff. So that's dependent on the development level. So based on this runoff coefficient, you can compute this ratio. So that's the infiltration LAD divided by harvesting LAD devices. Then you can look at the curve to determine this this ratio. Then you can determine how much percentage harvesting devices you need, how much percentage infiltration devices you need. So that's some very good research results that can be used by managers and engineers. Then we need to quantify these hydrologic processes. So engineers, when they design the process devices, so they need to quantify how much infiltration, how much evaporation, how much runoff. So they need to quantify this. So we have this called the 3-layer model. So 3-layer model. So this 3-layer model can be applied to any LADs. Can be applied for infiltration type, harvesting type, or hybrid type, any type of LADs. So this differential equation to describe this water balance in different layers. The first layer that we call the surface layer. So this we have this runoff from different surfaces. Then we have this rainfall. Then we have the evaporation, and probably we have overland flow and also infiltration. So that's a major component in the first layer. Then we have the soil layer. Soil layer receives the water from a surface layer, and also we have this transpiration by plants because we have these roots in the soil layer. Right? So this can transfer water from the soil layer. Also, we have this percolation. So that's water infiltrating into deeper soil. Then this we have a storage layer. Usually this gravel, we have used the gravel materials or materials can store lots of water. So that's storage layer. Sometimes we install these other drains so that we can prevent this flooding or these larger storms. Sometimes we don't build these other drains. So for this one, we have this percolation, this infiltration into native soil. Then we have this storage in this layer. Then probably if you have a drain constructed, that's a drainage. If you don't have drain, we don't have this drainage. So these are differential equations to describe these relationships of the different components of the hydrologic process. So we don't need to go through these equations here. So how do we use this 3-layer model to model different LADs? So for green roof, we need to use all 3 layers. But for green roof, usually we don't have this drainage system. So most time we have this surface layer, soil layer, and storage layer. So that's a green roof. Rain garden, usually we don't have a 3rd layer. We just have a surface layer and a soil layer. Bioretention pond, all 3 layers need to be used. Infiltration trench, we use all 3 layers. Bioswale, just the surface layer. Porous permeable pavement, all 3 layers. Rain barrier, we just use a storage layer. So for storage tank, we don't have a surface layer and a soil layer. We just have a storage layer. So that means we can use the same model to model all types of LADs. So that's great, right? So that we don't have to build different models for different LADs. So this is first research example here. So we monitored a retention pond. So this retention pond has 3 inlets. So this inlet collects stormwater from these streets, and this collects stormwater from this residential area, and this collects stormwater from park. And we used these different sensors. So we use the pH sensors, turbidity sensors, phosphorus sensors. We use the different kinds of sensors to continuously monitor this water quality changes. So this we did this monitoring works for 1 year. That's the entire year, so that we can capture this warmer season, cold season. So this rainfall events occurred in this year, and this flow hydrographs from these different inlets and outlet. So this one that's a flows for this storm event. So this is one storm event here. So you can see this outflow, this inflow from I think this is from street, and this is from residential area. This is from park. So this flow hydrographs from different land uses. So this is runoff reduction. So you can see this pond can reduce up to 8% of runoff. So that could be significant. Reduction. So this shows this water quality improvements by this pond. So this inflow. So the inflow, we have total suspended solid concentration. So you can see this outflow that significantly reduced. So this is scale that's from 0 to 20, that's 0 to 150. So that's significantly reduced. And total nitrogen concentration that's also significantly reduced. So we removed this peak. So that's very important. Total phosphorus reduction effects by this pond. And this one, that's temperature in this pond, dissolved oxygen, this organic phosphorus, this turbidity. So that's it in this pond. And this one, that's temperature at the different water depths. So we monitored all these water quality parameters in the pond, and also we evaluated the effects of the pond in improving this water quality. So this is removal efficiency over the pond. So you can see here TSS during this cold season. I think this inflow. It's an inflow. It's an outflow. That's a cold season. That's a warm season. So you can see TSS can be significantly reduced. Lots of these particles can be removed by this pond. So that's important. Total nitrogen. So this is warm season, more efficient than cold season. This is total phosphorus efficiency. So that's for cold season. That's reduced. This particle size. Some larger particles will be removed by the pond. Can be trapped in the pond. Another project we did this monitoring of stormwater quality versus different land uses. So we monitored the stormwater quality from this 6 type of this land uses. So the commercial, low density, open space, high density, transportation, and the industry. So we did this monitoring works in Virginia Beach. That's a city close to Norfolk. So this flows during our monitoring works. So this shows this monitored water quality parameters from these different land uses. So you can see sometimes this open space has a larger total suspended solid contribution. And this one, that's probably total phosphorus, open space, and this one probably total nitrogen. So that's mainly contributed from transportation. So this is statistical analysis to compare if the contributions from different land uses are different or not. So this means this for this TSS, that's mainly from open space, that's different from other type of land uses. So these 3 type land uses are different from this residential commercial. So this is just a statistical analysis to make a comparison to see if these different land uses have different contributions to different water quality components. Third project, we did this modeling study to see how this sea level rise affects the coastal hydrology. So this shows this sea level rise in Virginia Beach, Norfolk area. So you can see this before 1983, sea level was increasing by 3.9 millimeter per year. But the recent years, that's accelerated to 5.8 millimeter per year. So we have a big concerns about this sea level rise in coastal regions. It seems some articles say Sydney and Melbourne will be flooded if we have these sea level rise issues. And the only city will be left is Canberra. So that's an exaggeration, maybe worst scenario. So I did this modeling study to see how this sea level rise will impact this hydrology in this area. So this peak discharge will be dramatically increased at different years. After 100 years, you can see this will be increased from current roughly 3 cubic meter per second to 18 or 17 cubic meter per second. So that's a dramatic increase. The peak discharge will be increased. Also, the groundwater will be affected. So currently, the groundwater discharges into the ocean. So the flow discharging into the ocean at this location. But if this sea level rises, so you can see this groundwater discharge will be retarded. This will cause this flooding from this raised water table. So water table will be increased. That could cause these flooding issues. In particular, these underground infrastructures. We have these cables, utility lines that could be flooded. Also, this intruded salt water could cause this corrosion of these facilities. So that could be a big concern in coastal areas in the future. So what are the research needs in this field, stormwater? First, we need to have more monitoring data. So we need to monitor these different LED devices to determine their efficiencies, removal efficiencies. Also, we need to develop this planning design guides for LEDs because the engineers need to have some guidelines. They can't do the complex things like researchers. They don't have time, they don't have resources to do this complex researches. So researchers need to develop the guides based on the research results so that engineers can use these guides to design these structures. Then also we need to consider effects of climate change and the sea level rise. So this probably that could be a big problem in the future, climate change impact. Also develop new LEDs for treating emerging pollutants. So we have the emerging pollutants, so we need to figure out how to design these devices to remove these emerging pollutants. Then we need to monitor the impact of solar farms on stormwater quality and quantity. So you know this, we have the green energy and the solar energy is growing very rapidly in recent years. And we need to convert many acres land into this, we call this solar farms. So this could cause some water quality issue, water quantity issues. So we need to look at the impact from this solar energy development. So this shows some simplified illustration of the hydrology processes in these solar farms and possible solutions for treating this stormwater. Currently, you see this in USA, they have these solar farms. They cause lots of erosions, cause lots of these water quality problems. So they needed to have some scientific information to regulate this. So the conclusions. Our ADs with higher infiltration collection rate is preferred. So we like to have these LED devices that can facilitate infiltration. The treatment efficiency of LED devices is positively related to storage capacity and infiltration. So we need to have LEDs with sufficient treatment efficiency. You cannot just build a facility with very low removal efficiency. So that's not acceptable. Also, the scenarios with multiple LEDs is always more efficient than individuals. So most time we use this mixture, several types of LEDs combined together to treat the stormwater, not just the single type LEDs. For a scenario consisting of multiple LEDs, its overall treatment efficiency usually that's higher than this individual type of LED devices. Also, we need to have more research to consider emerging pollutants and these solar farms, also this climate change and sea level rise. So these are all big research topics in stormwater. So that's my presentation today and the questions. So these two books that Lars mentioned, so that's due to COVID. So the COVID 3 years, I don't have other, I couldn't go anywhere. So I just stay at home to the book. So that's a benefit for these 3 years. So this picture, that's from Fulbright Scholar presentation, that's Dr. Carrie Bennett. Is the executive director of the program. Okay, thank you very much.
Thanks very much. We have time for a couple of quick. So stormwater wetlands and ponds, one of the challenges we have here is that private developers develop the land and they make money out of it. They then build the stormwater assets, but that passes to the local government to manage. And so you have a problem that there's the income has gone to the private developer, but the cost of maintaining these assets is fallen on local government. And so they're now actively opposing, in some cases, these stormwater interventions because they don't feel like they can't afford to maintain them. That's the. How does it work in the US? Who pays for looking after those things once they're built?
Sure, that's a good question. In USA, so they build this small pond in a community. So if you drive to the community, you can see almost each community has this stormwater treatment pond. So this pond was contracted by city, and but owned by owners, by these different people. So the people who live there, and the owners need to report any problems to the city. Then if they find some problems, the city are responsible for this maintenance. Also, the city provides some subsidies to the owners, the residents, they provide some subsidies to them. They mow the grasses surrounding the pond. They are responsible to reduce these pollutants discharging into the pond. So they don't dump the trash into the pond. They don't dump this pesticide into the pond. So they are responsible for all these things. But the maintenance cost is bared by city.
It's an interesting reflection for Canberra. It's that Canberra is one of the only cities in Australia where you don't pay a stormwater levy as part of the rates. Yeah. So most around this point you pay a change tax.
Yeah, I think it's better to rely on the residents. So residents need to own the pond because this pond can provide some recreation for them. So they can have this barbecue party near the pond. So that's good. So they need to own the pond so that they have responsibility to maintain the pond. To help
so
you.
Richard, if you could clean up our role this weekend. Conversation, the GP will be going over to next week. I'm teaching it. So I've just sent you an invitation if you want to come along to the class, even just to listen and chat. It might be interesting. Yeah, a lot of this sort of stuff.
So that's which day?
I've sent a message, but it's on Thursday afternoon.
Okay.
So see.
Okay, that works. So the afternoon works. Thank you.
It's a very interesting walk.
Yeah.
Overuse. Did I use overuse?
No, it was all good. Yeah. I'm just.
Yeah. Some of the first years. All the students every day. No, yeah. Are all born after 2000. Yeah. Makes me feel old. Makes me feel really good. Okay, so we get once.
I'm just trying to figure out, I hit the Zoom so well that it's disappeared, like. I can still see, well, I could see everyone still there, but I can't figure out how to stop.